research and great tour. The facilities here are fantastic. As Bert mentioned, this project began at DuPont at their corporate catalysis center, and we started in 1997. They had an interest in converting methane to syngas and then doing Fischer-Tropsch chemistry. And they were trying to build up a catalysis effort for the first part of the reaction, methane to syngas, and I came in and joined the corporate catalysis center. At that time, it was DuPont, and then roughly year 2000, they did an IPO and spun Conoco off. So if you follow the news, Conoco has moved forward in their development. They've run a pilot unit. They'll announce plans for commercialization. So this or similar work should be shortly commercialized. So today I'll be telling you about a catalytic system that's been in the patent art now for a number of years. They've had probably a couple of dozen patents issue on syngas. DuPont has primarily patents with non-rhodium catalysts because there's a lot of patent art already out there from other competitors such as Shell, Lanny Schmidt, and University of Minnesota has a patent on a rhodium catalyst. So one of our early initiatives was to find a catalytic system other than a group 8 metal that could conduct this chemistry so that they could generate their own IP. So we identified, and you'll be hearing today, nickel-based catalyst. You'll learn about its preparation, how we tested it, its performance, some of its characterization, and then to make it into more of a commercial reality, how do you transform it into a three-dimensional structure? We did a lot of our initial screening as powders with the catalyst for higher throughput, and very limited information on catalyst life and a summary. Okay, probably you're very well aware that approximately 75% of the world's proven reserves in natural gas are found in areas that are remote, very hard to take advantage of their commercial viability. You have to basically convert it to something transportable. DuPont and Conoco identified this need. They had a natural gas refining program that they aggressively began in 1997. And their idea was to convert the gas to liquid fuels. And as Bert mentioned earlier, some of the approaches done in industry that they attempted was oxidative coupling. A lot of industrial research labs tried to tackle that one, but that can be rather challenging. And even today, oxidative coupling has not been commercialized. So this looked like a very attractive route, and certainly a lot of strong economic drivers. Basically, half of your capital is going into producing the syngas. So if you can find a more economical way of conducting that, you're ahead of the game. And our feeling was that you could save a lot on the technology by conducting it in what we call catalytic partial oxidation at the really second contact time, because then you're really shrinking down your reactor size, you have a high throughput rate. It seemed to be the way to go. So the catalysts that we developed were designed for those purposes, and you'll be hearing more about it. Most of the commercial industry uses steam reforming, and you can also reform methane with CO2. They call it dry reforming. And as I mentioned, our approach was to do partial oxidation. This looked very attractive. You got the preferred ratio of CO to hydrogen. Also, it has the advantage of being slightly exothermic, whereas the other two approaches are endothermic. Another problem with steam reforming is that you can build up quite a bit of carbon with a nickel catalyst, and you don't have necessarily the hydrogen to CO ratio that one needs for the Fischer-Tropsch. lower selectivity. The dry reforming, as we mentioned, it's endothermic, so it's going to cost you an energy. But it's higher CO selectivity, and then you are getting the ratio that you want. It can suffer again from rapid aging due to coking. And since our initiative was to look at the non-group 8 metal catalysts, nickel would be problematic. We like the partial oxidation approach. It's mildly exothermic, should be energy efficient, and we get the right hydrogen to CO ratio. So our major concern was to control the coking and eliminate some of the typical problems of deactivation and plugging. So you have a lot of reactions that you have to contend with. Of course, the desirable one is shown here, but you can also be generating CO2 and water. These are your exothermic reactions. We talked about reforming. There's some water-gas shift going on, and of course, product oxidation that you have to concern yourself about. And for carbon formation, that can occur due to the methane decomposition, the CO disproportionation, and the Syngas reaction. So DuPont had a strong technology in HCM production. They're a major producer of that, so they had a lot of expertise in millisecond contact time, and they felt comfortable with this approach. And there's already known out in the technical world the Ostwald process, nitric acid formation, converting methanol to formaldehyde. So there's certainly a track record out there for thinking of a millisecond contact time. Basically, you want to make it favorable to go to A to B and not continue on to C by optimizing the residence time. And doing that with high velocities, you can get the mass transfer that you need. And then minimize unattractive homogeneous reactions. So the benefits are you can achieve high conversions, high selectivities at a high throughput rate, therefore you can minimize your reactor size and yet be able to handle the heat and control the thermal runaway, prevent thermal runaway. So we designed and built a number of millisecond contact time reactors for our initial catalyst screening. Primarily on the left you have the gas manifold system. This goes on over to the reactor itself. We had it in an explosion-proof encasing. The product goes over to online GC, and then we would flare only a slipstream would be analyzed, and then we would flare the remainder of the gases. That was a requirement of the state of Delaware. And then we had lots of safety controls here in terms of redundancy for over temperature, over pressure, constantly monitoring the methane to oxygen ratio and so forth to be able to run safely. And then looking at more from a schematic viewpoint, in terms of we monitored the preheat. We had a number of thermocouples. The reactor was well monitored, its temperature. We had CO, oxygen, and hydrocarbon sensors tied into the safety of the unit. Constantly took the ratio of fuel to oxygen. Starting up, we ran not only methane for oxidation, but we looked at ethane and propane for the oxidative dehydrogenation activity. And a lot of times it was beneficial actually to begin the unit up under propane because the catalyst would ignite at a lower temperature and then you could slowly blend out the propane and replace it with methane. And so all of this was automatically controlled with a program to safely get you up to your running conditions. So we pack our catalysts as a monolith shown here, and it's sandwiched in between two ceramic foams, and that is to help to maintain the heat within the catalyst bed to prevent the heat loss. The entrance feed would come in from above. We would have alpha luminous spheres to basically take up the dead volume, minimize the homogeneous reactions. Monitored a lot of the preheat area, and also right below the catalyst bed we monitored that temperature, and further down there's a quick drop off of temperature. So showing what some of these foams would look like with and without the metal, the nickel on there. This here you have is the ceramic foam uncoated above and below the bed, and here's with the catalyst support. We would wrap the arrangement in a ceramic blanket and then slide it into the quartz tube reactor. That gave you a good fit. You got minimal bypassing. So typically when we're doing our screening in the beginning of the program, a lot of times if you really didn't need a whole lot of catalysts, you could charge anywhere from 0.2 to 2 cc's of a 2030 mesh material. We had 2 different feed scenarios that we would run typically. And we could go up to about 1 million gas hours base velocity. The feed, we would preheat the feed to get the reaction going, 500 degrees C. And typically, the catalyst that you'll be hearing about today would run up to about 900. Now, the Group 8 metals, they typically, the work that Laney Schmidt has published, they would light off at higher temperatures and generally operate around 1100 degrees centigrade. So it was rather straightforward preparation. We used wet impregnation. In our case, we did a lot of our work with MgO, and we also prepared catalysts in 3-dimensional forms, and you'll be hearing a little bit about that. We could use a foam and impregnate it with a powder and then burn out the foam. We could impregnate the 3D structures, wash coat them. We even did vapor deposition studies. So most of the catalyst data you hear today will be nickel with a promoter and with an MgO support. Really, it becomes a solid solution, and you'll see the data for that. The methane conversion would be in the mid-90s. Quantitative conversion of oxygen, which is good for safety purposes, and attractive CO hydrogen selectivities. So we investigated a number of promoters. These are the ones that were claimed in the DuPont patent. Some of the better ones, the first 3, you'll see the patent data on that. But basically the role of the promoters, it would enhance conversion selectivity, essentially eliminate problematic coke, enhance the catalyst life. And it also gave DuPont freedom to operate because there was already in the open literature nickel on MgO. Professor Ruckenstein of Brookhaven, New York University, had already published some data with nickel on MgO, but hadn't recognized or published any data with promoters. How does this compare to the rhodium catalyst? First of all, there was already patents out there, but of course you're going to save a lot of money, economics. It provides a higher methane conversion actually at the feed ratio that we were operating at, and you could run cooler, which could save you money. And here's the patent data, basically with the promoters shown here versus without the promoters. And you can see that the striking increase in activity and selectivity. And basically with the 3 promoters under 1 day of operation, you're seeing no detectable coke. And you'll see later on, without the promoter, you can get up to 1 to 2% under comparable operating conditions. So we looked at the XRD of the nickel MgO, and basically when you make the catalyst, you take nickel nitrate impregnate it, wet impregnation onto the MgO, calcine it up to 800 degrees C in the air, and then prior to putting the syngas or the feed over the catalyst, you do a pre-reduction with hydrogen for 4 hours at 800 degrees C. So that helps to activate the catalyst initially, but at the same time you'll see some TEM data where it actually reduces the nickel. But the nickel oxide and MgO is essentially a solid solution. It's infinitely soluble. They have the same face-center cubic packing structure. So it's rather ideal for our needs here. So we only see the Periclase phase for the fresh, A. Now the spent catalyst, 2 theta angle roughly at 52, you can see a little bit of the nickel metal coming in, and this is after, without the promoter. And then shown here, we've now added the manganese at very low levels, and the manganese oxide also forms a solid solution in MgO. And we're seeing only maybe a very trace amount of the nickel metal showing up in the XRD. The manganese, you can't really detect any crystalline phase there. Without the promoter, we have some TEM images here for the fresh and the spent. And even because we do that pre-reduction step, we're generating some nickel metal, maybe like 30 nanometer diameter particles. And then after being spent, of course the nickel's there, it's sintering a little bit. You see a little bit of carbon nanostructures showing up. And again, without the promoter, looking at the spent material, the carbon nanofilaments, and it literally encapsulates the nickel particles. Here we have the manganese promoted catalyst, and we don't see any detectable carbon when we do the thermogravimetric analysis, but under inspection, if you look around, you can see little things like carbon nanotubes showing up, but nothing that is really problematic in terms of operation. And every once in a while you'll see a nickel particle, although it's a lot smaller than the ones that you saw earlier, on the order of 10 nanometers in the encapsulation of the carbon after reaction. And here's just another picture. It's just kind of interesting how we were seeing this carbonaceous chain-like configuration there. So we had beam time. We had an opportunity to do X-ray absorption of the fresh and spent catalyst sets, and we're able to measure, how much nickel, 0, nickel +2 is present, but looking at the absorption edge. And that will tell you basically something about the oxidation state. And so that was very instructive. We were seeing large concentrations of reduced nickel when there wasn't any promoter, and that would be associated with the carbon deposition. With the manganese there, that's generally not the case. And so it was a nice confirmation with our TEM work, providing us with the same conclusion. So here you can see the blue line here would be the fresh catalyst of manganese. So we're seeing no detectable, what are we looking at here, nickel metal. And then with use, about 0.6% of the nickel gets reduced. Whereas the fresh catalyst without the manganese, you're going in with already 16% nickel metal, which you saw in the TEM. And then after use, and we're talking about a day of catalytic use, you're already having 44% of the nickel reduced. So this gave us instructive information. And we also looked at the manganese, because we were interested in what oxidation state the manganese was in. And the data would support that the fresh catalyst would be in a manganese +3 oxidation state, whereas the spent was a +2. So the manganese is undergoing reduction. And as far as looking at what happens after the catalyst is used under 8 to 10 hours, the data fits would support the conclusion that perhaps a manganese oxycarbide is being formed. Although this isn't conclusive, it would be in support of that information. And just using molecular modeling, we had a program called Sirius. We're interested to see, okay, how would the manganese be distributed within the nickel MgO solid solution, fairly evenly distributed, whereas after use, it would support the fact that perhaps you could be forming a manganese oxycarbide and that it would move up to the surface of the catalyst. So a lot of this would be an interesting problem to pursue further. In other words, why is it that the manganese helps to maintain the catalyst, keep the nickel reduced, and minimize coke? So here we have a structural model of looking at the nickel phase within the catalyst system, just showing you that it's fairly well-ordered solid solution, basically. Again, supporting evidence through modeling. All right, so we did a lot of, the program began with a lot of screening, identifying opportunities of where to develop new catalytic systems that would be competitive with rhodium. We felt like we were comfortable moving forward, in this case with a manganese promoted nickel MgO. We wanted to get it into a more practical three-dimensional form. And one approach that we did was to form reticulated ceramic foams. So basically taking the powder, putting it into a porous polyurethane, filtering off the slurry, drying it, calcining it, basically at relatively high temperatures to give it mechanical strength. So we ended up with a form that was roughly 80 ppi and of the diameter and length appropriate for our quartz reactor. And that was one approach, and we looked at other synthetic approaches. Impregnation, taking alpha alumina foam. We looked at with and without the promoter for comparison. XMET, that's a company that offers nickel metal, and we were able to design, basically perforate the nickel metal into putting holes in there to give preferential flow patterns, and then we would stack 19 of the discs together. And prior to running, we would do the hydrogen activation step that I mentioned earlier. Another approach was to take what's called iron chrome alloy. You can take that and calcine it to 1100 degrees C and form an aluminum oxide overlayer. And then on top of that, you can vapor deposit with, we collaborated with the University of Delaware to do this work, to add on the nickel and the magnesium, oxidize it to the oxide. And again, we would have these as perforated structures and stack them. And we did some modeling to tell us, what would be the best arrangement for preparation and rotation of each of the discs. We've got partially stabilized zirconia. There was a lot of good press about this being a preferred support for rhodium. So we thought, okay, well, we should investigate that as a support, which we did, either as an impregnation or a wash coat. And then we already talked about this reticulated foam. And then the honeycomb, that's cordiorite that you could get for like catalytic converters. Very economically viable. It's good for heat shock. You can go cycle up and down in temperature and have good integrity. So again, the data that's out there in the patents are shown here. You may not remember what A through H are, but basically the data is saying that you can support these nickel catalysts on a three-dimensional form. It looks very attractive because we're getting reasonable conversion selectivities. A is the one that was nickel without the promoter, so we did see quite a bit of coke forming there. And I forgot what E was. I can go back to that one. Oh, this is the partially stabilized zirconia support, and we found that to be problematic actually. So that turned out to be not preferred in the case of nickel, unlike rhodium. But it looked good, and we were getting data that was fairly comparable to the powder, so we felt good about our powder screening program because, you know, that was a good for higher throughput and finding new compositions for our reaction. It worked out well, and then we could take the preferred materials and move them into this type of a program. All right, so overall comparison within the 3D structures. The reticulated foam, we like this one quite a bit. It could run, it had some of the lower run temperatures. It ignited lower, ran lower. We thought that would be good. Had very little coke. And then you don't have to worry about the support effect because the catalyst itself is the support. The honeycomb looked very attractive too, due to its low cost and also good thermal shock resistance. So we moved forward with those and what we called a very limited, more on the 3D structures. Here we have the thicker alloy. This is a very novel composition. You don't see this too often in the patent literature, using this as a support, cost effective. That one panned out well. We weren't too high on the partially stabilized zirconia or the alpha alumina because we did see some nickel aluminate forming, which would be bad. That would cause the catalyst to deactivate and coat. All right, and these so-called life studies are very short actually, but for 24 hours we have data here for you to look at. And basically you start off, the catalyst will light off and eventually stabilize at a higher temperature, somewhere between, in this case, 800 and 900. But under this limited testing period, we didn't see anything really negative happening. And that was for the reticulated foam, and the other catalyst that we were pleased with, we ran it for a similar time period. The honeycomb, in this case it was wash coated on there, and likewise had fairly good stability. The temperature, albeit, was declining over that time period. So in summary, we've been able to achieve our target conversion selectivities with a nickel MgO, and then adding the promoter in there, we get improved performance, as you saw. The coke formation was minimized, saw very little precipitation. Be interesting to go back and understand that mechanism further. All the components are in a solid solution, and definitely alloying the manganese in with the nickel and the MgO helps to stabilize the nickel in the +2 oxidation state, which is to our benefit. And then basically being able to take the powdered catalyst, transform it over to a 3D structure, which would be necessary to move on to the next phase. And this was a team effort at DuPont. We had lots of people working in synthesis, working on the reactors, catalyst characterization. People were doing modeling, and it was just a pure pleasure, a very collaborative program. And at the same time, they were addressing other catalytic approaches, group 8 metal and so forth. So it turned out to be lots of fun, and they've basically acquired the technology when they did their IPO. All the patent rights and the programs shifted over to Conoco, and they continued to work on that at Ponca City. So maybe in the future you'll hear more about it when they're But right now, they're probably busy with their commercialization. And if there are any questions. Yeah, sorry.
Thanks, it's very interesting review. You focused on the catalyst quite correctly. Would you comment perhaps on the scale-up, without getting into proprietary stuff, but what concepts would you be looking for to scale up millisecond reactors? We're aware of this sort of gauze type, say, platinum or silver gauze, but scaling up is going against the idea of milliseconds. And I think Lanish did have a difficulty that also small-scale stuff was pretty good, but couldn't really get it out of the lab.
Right. It's very challenging, and that's where good engineering comes in. They had to do a lot of safety risk factors because there's a strong potential to go into the flammable explosive zone in no time. And of course, even on our little scale, we were very worried about that. We had to have lots of redundancy and measurements and so forth. And scaling up, it only magnifies it. And one thing in your favor, actually, is that the speed of the feed is greater than the flame speed. And that you can take advantage of that in your design. You can have flame arresters. And that, I'm sure, most likely would be incorporated into scale up. And then the other thing is how to scale up some of these catalysts, because, just having a gauze is challenging in itself, and getting that to ignite properly. So, I'm sure one would need to talk to commercial manufacturers of these type of foams, Corning or Johnson Matthey would be experienced, Engelhard. And then for scale up, you're not talking about something huge. It's probably 8 feet in diameter. But most likely you would have to piece it together. You probably couldn't have a continuous ceramic piece for that. So it isn't trivial by any means. And I don't know which approach they eventually took, but somehow they managed to overcome the hurdles.
Your results here were at ambient pressure.
Right, and that's the other thing. Yeah. Scale up, you got to be up at elevated pressure, and it becomes a whole new challenge. And then, it's hard to maintain these selectivities at higher pressure too. Right? But economically, you have to be at elevated pressure. Yeah.
How does the coke buildup comparison compare between the catalysts that are not promoted with manganese and the ones that are promoted with manganese? And I know that addition of certain oxide components to certain platinum catalysts, like platinum tin catalysts, have been used for the CO2 reforming and methane, like the dry reforming. And the oxide component was, I guess, proposed to assist in cleaning the coke off of the surface.
Right.
Do you think that something like that could be working here?
I think that's really logical, because if that model says you have this manganese oxycarbide thing, maybe that's what it's doing. Is, the carbon that does show up, it sort of does a redox on it and gets it off the surface. I also think, if we had I don't know how you go about it, but I think somehow the manganese must be interacting with the nickel also, and it could have a redox coupled intimately close to it that it could influence the oxidation state. Yeah, that's an excellent idea. Yes.
Can you comment on the sulfur sensitivity of these catalysts?
I don't know, because we used clean methane, and again, that's very important for scalability. I'm sure probably when they move this program to Ponca City, that had to be a factor for them. That could really, maybe even for the rhodium catalyst, that could be an issue too. No.
Rhodium's not so bad.
Yeah, nickel will be.
Yes. The deactivation, there's no deactivation, but in some cases, some coke build up there, and then when you compare the A to H and stopped after 24 hours, it's probably difficult to say which one would last longer in a more pilot unit compared to micro reactor that I'm using here. So did you look at long-term deactivation? If there is any, over a period of days rather than just one day?
Yes, they
Have you-
continued, but I didn't do it personally, but
But
it
been
moved
going on.
into that, for weeks, basically. Yeah, you can't really conclude too much here, you're absolutely
Yes,
right.
fine.
But you can see some dramatic effect, that, 1% to 2% coke
Right.
versus less than 1.
So what happens after the coke build-up? Going to regenerate, recycle, or you?
Yeah, I don't think we had any regeneration. Like, can you burn the coke
Yeah,
off, come
yeah.
back? Yeah, I don't have that shown here. Can't really comment on that right now.
You also mentioned that growth of crystallites,
Mhm.
magnesium, I think, with time. And if that happens, it may be difficult to bring the activity back, even if you
That's right.
regenerate. So how do you?
You wouldn't be able to, without, like the nickel oxide MgO catalyst. Once you get these things that are 30 to 50 nanometers, I think you're done. So you don't want to go that far. Yeah, that would be hard. But let's say with the promoter, we didn't see anything negative, but we don't have the data here to show you. If you run for a week, it's, is it a problem, and can you correct it? Maybe that type
Right.
of coke you can fix.
Right.
Right.